Hello guys, welcome to Buddy Academy. Me Priyanka going to teach you important topics of each unit in your grade 12 chemistry. So today in this session we are going to study the first chapter, that is the solid state. Under that we are going to study the important topics and also some important problems based on this unit. So the weightage of this chapter is only 4 marks. It is a very small unit in your grade 12 chemistry and it is very easy to score marks in this unit. So the important topic in this unit are crystal lattice and unit cell, calculations involving unit cell dimension and imperfections in solid. So without any delay, we'll move on to the session now. What is solids? You may know already what is a solid and then what are the properties of a solid. So solids are classified into two types, crystalline solids and amorphous solids. Based on the arrangement of constituent particles, they are classified. Okay. So crystalline solids have a regular pattern of arrangement of particles, whereas the amorphous solids do not have a regular pattern of arrangement of particles. So the example of crystalline solid is quartz, whereas in example of amorphous solid is quartz glass. So from your exam point of view, there is a chance of asking the difference between crystalline and amorphous solids, or for they can ask an example for the crystalline and amorphous solids also. So now let me discuss about the properties or characterization of the crystalline and amorphous solid. So properties of crystalline and amorphous solids. So crystalline solids have a definite characteristic geometric shape, whereas the amorphous solids have an irregular shape. And then the melting point, crystalline solids have a sharp melting point, whereas the amorphous solids have a gradual soften over a range of temperature, because the particles are not arranged in a regular pattern. So there will be a wide range of temperature. Okay. And next is the cleavage property. When you cut a crystalline solid with a sharp edge tool, they split into two pieces and the newly generated surface are plain and smooth. Okay. Whereas the in amorphous solids, when you cut with a sharp edge tool, they cut into two pieces with irregular surfaces. And next is the anisotropy nature. Okay. And next is the order of arrangement of crystalline and amorphous solids. In crystalline solids, the order of arrangement will be a long range order, whereas in amorphous solids, it is only a short range order. So these are very important from your exam point of view, because they can ask in 3 marks or also as a sub question in a 5-mark question, difference between crystalline and amorphous solids. You must know about at least 4 to 5 difference between these two solids. Okay. And again there is a chance of asking another question, the anisotropy nature. So what is anisotropy? Okay, that is the arrangement of atoms. Anisotropy is the direction dependent. Okay, whereas isotropy is the direction independent. Okay. So next is the polycrystalline solids. This is also one of the important question, because it has both crystalline and amorphous nature. So they are polycrystalline solids. Okay. So next we will see about the crystal lattice. So first of all, what is a crystal lattice? It is an symmetric three-dimensional arrangement of atoms, ions or molecules. Okay. So you know that in a crystal lattice, you can able to easily observe that a repeated pattern has been multiplied n number of times in a crystal lattice. So that one particular repeated pattern is the unit cell. So what is an unit cell? It is the smallest portion of a crystal lattice. Multiple times of unit cell will make a crystal lattice. So in this, the atoms or molecules or ions are arranged in a regular pattern, and these atoms or ions are represented as points, and these points are known as lattice sites or lattice points. So these are the atoms. These atoms are joined together by a straight line to form the geometry of the crystal lattice. So these are the atoms, and then these are represented as points, and that is known as lattice point or lattice site. So now we will see about the parameters of a unit cell. So there are totally 6 parameters in a unit cell. Among that, 3 are axial distances and 3 are axial angles. So axial distance are nothing but the distance between the one atom and the other atom is the axial distance. Okay. So here there are 3 axial distance, A, B, C, and 3 axial angles, alpha, beta and gamma. So you can able to easily note down that. So A, B, C are the axial distances, and alpha, beta, gamma are the axial angles. So the angle between AB is gamma. You can remember in this way, the angle between AB is gamma, AC is beta, whereas BC is alpha. So this, though you change the position of A, B or C, the angles between AB will always be gamma, and the angle between BC will always be alpha, and the angle between AC will always be beta. So next we are going to see about the classification of unit cell. So unit cell are classified into two types, primitive unit cell and centered unit cell, and this centered unit cell is again classified into three types, body centered unit cell, face centered unit cell, and then end centered unit cell. So before seeing what are these types of unit cell, we are going to see in unit cell what are all the in what are all the possible ways an atom can be arranged in an unit cell. So this is the unit cell. An atom can be occupied at this position, and this is known as the corner of unit cell. So corner atom, okay. And this one is the edge, okay, edge of the unit cell. An atom can be occupied at the center of edge, known as edge centered atom. And then this is the face of an unit cell, okay. So this one is the face of an unit cell. And also an atom can be occupied at the face centered, okay, and that is known as face centered atom. And then atom can be occupied at the center of body, known as body centered atom. And then the diagonal in the face is known as face diagonal. And then the diagonal in the whole unit cell is known as body diagonal. So now we are going to see about the types of unit cell. So in primitive unit cell, the atoms can be occupied only at the corners of the unit cell. And then next is the face centered unit cell. Along with the corner of atoms, the atoms can be occupied at the center of all the faces, and that type of unit cell is known as the face centered unit cell. And next is the body centered unit cell. Along with the corners of the atom, along with the corners, the atoms can be present at the body centered also, and that type of unit cell is known as body centered unit cell. And next one is the end centered unit cell. In this, the atoms will be present at corners and also at the face of any two opposite face center of any two opposite faces, and this one is known as the end centered unit cell. So now we are going to see about the contribution of atoms, okay. So we saw that the atoms can be occupied at the corners and also at the edges and also at the faces and then at the body centered. So we are going to see about the contribution of atoms at that particular position. So first, the atoms can be occupied at the corners, okay. So totally how many corners are there in an unit cell? Totally 8 corners. 1, 2, 3, 4, 5, 6, 7 and 8. Okay, so 8 corners are there. So on each corner is being shared by 8 unit cells. So the contribution of the particular position is 1 by 8. Okay. So the number of contribution of atoms in the corner position is 1 in the primitive unit cell. And then face centered unit cell. So contribution of face centered atoms are totally 6 faces are there in an unit cell. So 1, 2, 3, 4, 5 and 6. Okay. So totally 6 face centered atoms are there in an face centered atoms are there. So the each face is being shared by 2 unit cells. So the contribution is 1 by 2. So the contribution of atom is 3. And then is the edge center. So totally there are 12 edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. So totally 12 edges are there and each edge is being shared by 4 unit cells. So the contribution of atoms at the edge contribution of edge center atom is 3. And next one is the body centered atom. So the body centered atom is not being shared by none of the unit cells. So only one body centered atom is there. So it is not being contributed to any other unit cell. So only contribution of body centered atom is 1 to an unit cell. So now we'll see about the number of atoms in each unit cell. So in primitive unit cell only atoms are present at the corners, okay. So only 8 atoms are there at corners, and then the contribution of the corner atom is 8 into 1 by 8. So answer is 1. So the number of atoms in a primitive unit cell is 1. And next is the number of atoms in the body centered unit cell. So in a body centered unit cell, the atoms will be at the corners and also at the body centered. So the corner atom contribution is 8 into 1 by 8. This is one contribution, and next one is the body centered contribution. So totally the number of atoms in a body centered unit cell is 2. And next is the face centered unit cell. Hope you guys are able to understand this topic. And next is the face centered unit cell. Here the atoms are at the corners, so 8 into 1 by 8 again, and then at the faces, so totally 6 faces, and the contribution is 1 by 2, so 3. Totally 4 atoms are there in a face centered unit cell. And next is the edge centered unit cell. Here also the atoms are present at the corners, so 8 into 1 by 8. And next is the edge center. Totally 12 edge center atoms are there. Contribution is 1 by 4. So totally 3. So totally number of atoms are 4 in the edge centered unit cell. So now we are going to see about the 7 crystal system. So this is very important topic. So you can able to easily remember this 7 crystal systems by remembering one simple formula: CT, OT, HMT. C stands for cubic, T stands for tetragonal, and O stands for orthorhombic. T again stands for trigonal or rhombohedral, and then hexagonal, monoclinic, and triclinic. So here we are going to see about the axial distance and the axial angles. You may also ask in your exam, so what is the axial angle of this particular crystal system? And then also they can ask about the example of this crystal system. So first we'll see about the axial distance. So the simple trick to remember these things is, first you write the axial distances. So by remembering this formula, you can able to easily write this one. So first the axial distances of these 7 crystal system. First is the so the 3 axial distances are A, B, C, okay. So A is equal to B is equal to C, okay, this is first one. And next is one, A is equal to B but B is not equal to C. This is second one. And next is the A is not equal to B and B is not equal to C. So this pattern will be again repeated in the next 3 things, okay. And then the last one is also A is not equal to B, B is not equal to C. So by remembering this one, you can able to easily remember those 7 axial distance of 7 crystal system, okay. And next is the axial angles. So the first axial angle, for first 3 things, the axial angle will be equal to 90 degree. That is alpha is equal to, beta is equal to, gamma is equal to 90 degree. So for first 3 cases, this is same, okay. So in all the 3 cases, alpha is equal to, beta is equal to, gamma is equal to 90 degree. All the angles are 90 degree. And next in case of trigonal is alpha is equal to beta is equal to gamma but not equal to 90 degree. And next one is the hexagonal. Alpha is equal to beta is equal to 90 degree and gamma is equal to 120 degree. And in monoclinic, alpha and gamma is 90 degree whereas beta is 120 degree. Whereas in triclinic, alpha, beta, gamma is not equal to 90 degree. So none of the angles are equal to 90 degree, okay. So and then these are the examples of the 7 crystal systems. They may ask whether this they can give the example and they may ask you to identify the type of crystal, okay. Or they can give the crystal system and ask you to answer about the example for that, okay. So these are the axial distances and axial angles. Try to remember, this can be asked in your 1 mark questions. So next is the Bravais lattices, okay. So there are totally 14 Bravais lattices, okay. Based on this 7 crystal system, 14 Bravais lattices are possible. So for cubic there are 3 Bravais lattices, and for monoclinic 2, and then for orthorhombic 4, rhombohedral, and then this is for tetragonal, and this is for hexagonal and triclinic. So the most symmetrical crystal system is the cubic crystal system, and the most unsymmetrical crystal system is the triclinic crystal system. They may ask you about this also, whether which is the most symmetric one or which is the most unsymmetric one, okay. So next one is the close packed structures. We know that crystal lattice are arranged in a closely packed structure. So each atoms are arranged very closely to each other in a crystal lattice, right? So this arrangement of atoms in a crystal lattice can be studied in three steps. Okay, first one is the arrangement of close packing in one dimension, and then close packing in two dimension, and then close packing in three dimension. So first is the close packing in one dimension, means the atoms are arranged in a single row. Okay, so here the important point to note is the coordination number. Okay, so what is the coordination number? So coordination number is nothing but the number of surrounding atoms. Okay, so consider this is the main atom. Okay, this is the main atom. Okay, so how many atoms are surrounded to this atom? Two atoms are surrounded by a particular one atom, right? So the adjacent atoms to that is 2 atoms. So the coordination number of this is 2. Okay, they can ask what is the coordination number of these this particular arrangement of particular arrangement in one dimension. Okay, and next is the close packing in two dimension. Here there are two types of arrangement. One is the square close packaging and another one is the hexagonal close packaging. Okay, so first is the square close packaging. In this, the atoms are arranged one above the other. Okay, so here again the other important point to note here is the void. So what is a void? It is an empty space left behind when the atoms are arranged in a regular pattern. So this is the void. Okay, the empty space that is left here is the void. Okay, so this one is the void. Okay, so what is the type of the square close packaging? AAA type, because it is a similar pattern of arrangement of atoms. So this one is the AAA type, and the coordination number is 4 because on each particular atom is surrounded by 4 different 4 atoms. So the coordination number here is 4. Okay, so make a tabular column of this one, the coordination number and also the type, AA type or what. Okay, so the type of arrangement and also the coordination number. So next one is the hexagonal close packaging of spheres in two dimensions. So in this in this the first type of arrangement we name it as A. Okay, and again we are going to place the another one dimensional structure over the first one. Okay, but in this time what we are going to do is we are not going to place straightly above the first layer. We are going to place in between the space of the two atoms. Okay, so like that, in between the gap between, going to place the second layer in between the gap of the first layer. So this type of, so the second layer has been named as B, and this type of arrangement is AB type, and the coordination number here is 6 because the particular one atom is being surrounded by 6 atoms, 1, 2, 3, 4, 5 and 6 only. So the coordination number here is 6. Okay, so next is the close packaging in 3 dimension. So here there are two types. One is 3-dimensional close packaging from 2-dimensional square close packaging sphere. So we are going to place the square close packaging one above the other. So this type of arrangement is known as the AA type because all the arrangements are same, right? So this one is A type. Actually this first layer is the AA type and the second layer is also AA type, right? So like that, this is then totally an AA type. So the coordination number here is 6. Okay. So try to remember all the coordination number and also know what is the coordination number. Try to answer that questions. Okay. And next one is the 3-dimensional close packing from 2-dimensional hexagonal close packed structure. So this is also characterized into 2 types. Okay, placing the first step is the placing second layer over the first layer, and next one is the placing third layer over the second layer. Okay, first. In this one, the second layer is being placed over the first layer in the gap. Okay, in the space left between in between the voids of the first layer. Okay, so in that way it is being arranged. So we already saw about the hexagonal close pack structure. No, in that how the first layer and second layer are being arranged. So like that way, here also the second layer is going to be placed in the space left behind, like voids between the first layer. Okay, so in that way it is going to be arranged. So in that manner, the voids, the new void that is being generated when the second layer is being placed over the first layer, it is going to generate a new void. That type of void is known as the tetrahedral void. And again another void is being generated known as the octahedral void. This void is not being generated because of the space left between the first layer or the second layer, because in that case none of the atoms are going to be placed on that particular position. Okay, so the second layer is not going to be filled on that particular point. So that type of void is known as the octahedral voids. Okay, so totally two types of void in this case. One is the tetrahedral void and other one is the octahedral void. When you are placing the second layer over the first layer, a new void is going to be generated, that is the tetrahedral void. And sometimes the void is not being occupied by the first layer or also by the second layer. So that type of void is known as the octahedral void. Okay, so this is what I said already, tetrahedral void and the octahedral void. And then the number of voids. So first, to calculate the number of voids in a crystal lattice, we have to assume that in this case the atoms are arranged as are represented as spheres, right? So we are going to represent these atoms as n. Okay, so we are going to represent these atoms as n, and then the number of octahedral voids in a particular crystal system can be calculated by the formula n. Okay, and then the number of tetrahedral voids can be calculated by the formula 2n. So what we can able to understand from this, so the number of spheres is equal to the number of spheres is equal to the number of tetrahedral number of octahedral voids, and then the tetrahedral voids is the double the number of these spheres. Okay, so from this, based on this thing, you can get problems based on these things. Okay, so now we are going to see about the placing the third layer over the second layer. So on placing the third layer over the second layer, there are two cases. One is covering the tetrahedral voids and the other one is covering the octahedral voids. So the covering tetrahedral voids is an hexagonal closed packed structure. Okay, and this is the AB type of arrangements, and then here the coordination number of the of this type is 12. Okay, and next one is the covering octahedral voids. This type of arrangement is known as ABC type, and the coordination number is also 12. And then this type of covering octahedral void arrangement is known as the cubic closed packed structure or face centered cubic structure. So now next we are going to see about the packing efficiency. So first of all, what is the packing efficiency? It is the percentage of the atoms that are being occupied in a unit cell. Okay, so the space that is being occupied by the atom in a unit cell. Okay, how long it can how much space the atoms can occupy in a particular unit cell. So here there are the atoms can occupy different position, no? So based on that, they are classified into three types. One is simple cubic, and the other one is hexagonal close packing or cubic close packing, and next one is the body centered cubic structure. So there is a small derivation for this, how we are getting the percentage of percentage of occupancy of atoms in the particular unit cell. So for the simple cubic lattice, 52.4% of the space is being occupied by the atom, whereas in hexagonal close packed structure or cubic close packed structures, 74% of the space is being occupied in the crystal lattice by the atom. And next one is the in body centered unit cell, 68% of the space is being occupied by the atoms in the unit cell. So this derivation is also very important, but it is a very small derivation, but most of the times you can able to get get the problems based on this percentage alone. Mainly they can ask in 1 mark questions the percentage of this particular cubic lattice, like that they can ask. Okay, so but also try to read the derivations, you can able to easily solve it out. Okay, so and next one is the calculations involving unit cell dimension. So here we are going to see about the density. We are going to calculate the density of the unit cell. So first, you know what is the volume of an unit cell. So volume of a cube is actually, unit cell is similar to that of cube, right? So volume of a unit cell is A cube, and then the mass of the unit cell. So the mass of the unit cell can be calculated based on number of atoms in unit cell into mass of each atom. This number of atoms in unit cell is represented by Z, and the mass of each atom is represented by M. Okay, so the mass of an atom M can also be calculated by the formula molar mass by Avogadro number. Okay, so we know about the mass of the unit cell, and then we know about the volume of unit cell. So what is the density formula? In general, density is equal to mass by volume, right? So density is equal to mass by volume. We know that mass is equal to mass of the unit cell is equal to Z into M, and then the volume of the unit cell is equal to A cube. Okay, so first density is equal to what? Mass by volume. So mass of the unit cell is Z into M. The volume of the unit cell is equal to A cube, and thus the mass of the unit cell is equal to what? Molar mass by Avogadro's number, right? So Z into M by A cube into Avogadro number. So this is the formula for density of an unit cell. Okay. So based on this, you can get many problems. So in 3 marks, they can easily ask about related to density. They can ask questions which is very easy to solve, and you can also able to easily score from this. Okay. So next is the imperfections in solid. Okay, so the imperfections in solid means there is an distraction or deviation in the arrangement of atoms. So these imperfections in solids are classified into 2 types, point defects and line defects. So what is point defect? The irregularities or deviation from ideal arrangement around a point or an atom in a crystalline substance. So this is known as the point defect. So it is going to be a deviation in the particular point. Okay. So whereas in the line defect, the irregularities or deviation from ideal arrangement in an entire row. Okay, it is going to be the deviation in the entire first layer or second layer, like that, in the entire row. So this point defect, so main thing here is the point defects. Okay, so this point defects are further classified into 3 types: stoichiometric defects, non-stoichiometric defects, and impurity defects. So we are going to see individually about these 3 things. Okay, so first the stoichiometric defects. So what is a stoichiometric defect? In this defect, it is not going to disturb the stoichiometry of the solid. It is also known as intrinsic or thermodynamic defect. The stoichiometric defects are further classified into 4 types: vacancy, interstitial, Frenkel, and Schottky. Okay, so first we'll see about what is vacancy defect. So in a crystal lattice arrangement, we know that atoms or molecules is going to be arranged in a regular pattern. When some of the atoms are going to some of the lattice sites are going to be vacant in this particular defect. Okay, so when there is going to be any vacancy in the arrangement of atoms, then this type of defect is known as the vacancy defect. So there is going to be the vacancy, right? So what will happen when the atoms are going to be vacant? In this case, what will happen? The density of the substance is going to be decreased. Okay, so in case of what is vacancy defect? In this defect, the lattice sites are going to be vacant, and then the density of the substance is also going to be decreased. So this is one thing. And next one is the interstitial defect. So in this defect, what is that? There is not going to be any vacancy in the crystal lattice. There is going to be some constant particles that are going to occupy at the interstitial site. So what is the interstitial site? This is also an important thing. So what is interstitial site? So that is the space left in between the arrangement of a crystal lattice, right? So that is known as interstitial site. So here in this case, some other atom or some foreign atoms are going to be occupied in the interstitial sites. Okay, this type of defect is known as the interstitial defect, and in this case, what will happen? The density of the substance is going to be increased. Okay. And next one is the Frenkel defect. In this case, smaller ion is dislocated from its normal site to an interstitial site. So you can able to observe here the atom is dislocated from this position and is going to occupy in a new position. So there is not going to be any change in the density of the substance because there is no vacancy in this system. Okay, there is going to be a vacancy in its original position, but the atom is being occupied at the interstitial site. Okay, so there is going to be both vacancy and interstitial defect, but the density of the substance is not going to be affected, right, because it is being balanced now. So this type of defect is also known as dislocation defect. And next one is the Schottky defect. An equal number of cations and anions are missing in order to maintain the electrical neutrality of the lattice. Okay, so in this type, what will happen? The electrical neutrality of the substance is going to be balanced, whereas the density of the substance is going to be decreased. So vacancy and interstitial defects are mostly shown by the non-ionic solids, whereas the Frenkel and Schottky defects are going to be shown by the ionic solids. Okay, so this is one important point. Frenkel defect and the Schottky defect are going to be shown by the ionic solids. Okay, and next is the impurity defects. These defects will arise when foreign atoms are present at the lattice site or at the vacant interstitial sites. Okay, so there is going to be an vacancy in the original arrangement of lattice. Okay, so on balancing that, what will happen? Some other foreign atom is going to be occupied at the crystal lattice. So some some foreign atom with higher valency. So in this case, let me consider NaCl atom. So Na plus and Cl minus ions are going to be arranged in a regular pattern. So some of the Na plus ions are going to be vacant. Okay, so to balance this, what will happen? Some strontium ions are going to occupy that crystal lattice. So what will happen, this strontium ion is going to occupy the position of the sodium ion at one position, okay, and then this other position will be left vacant, okay. So what will happen now, the electrical neutrality is being balanced, that is the valencies are balanced because the valency of strontium is 2 plus, because only Na plus 2 Na plus atoms are being vacant, right. So the electrical neutrality of the crystal lattice is being maintained, okay, is being balanced. But what is happening here, one position of sodium plus is being left vacant, okay. And next is the non-stoichiometric defect. So till now we have seen some two types of defects, and in that there is not going to be any change in the stoichiometry of the crystal lattice. In this case there is going to be a change in the stoichiometry, that is the arrangement of the atoms, okay. Inorganic solids contain the constant elements in non-stoichiometric ratio due to defects in the crystal structure. Those non-stoichiometric defects are classified into two types: metal excess defect and then the metal deficiency defect. This metal excess defect is further being classified into two types. One is metal excess defect due to anionic vacancies, and then the metal excess defect due to extra cations at interstitial sites. So these are the two types, okay. And now we are going to see about the metal excess defect due to anionic vacancies, okay. So what is happening here, a negative ion, that is anion, is going to miss from the lattice side, leaving a hole in that particular crystal lattice, which is then occupied by an electron to maintain the electrical balance, okay. So in this crystal lattice, negative ion is going to be whole, okay, is going to be vacant, okay. So to balance the electrical neutrality in this case, an electron is going to occupy that particular position. Now what will happen, the electrical neutrality is being balanced, but the density of the substances is not maintained, okay, the density is lowered, okay. So this type of defect is known as the Schottky defect, and the examples of this is the NaCl and KCl. And next one is the metal excess defect due to extra cations at interstitial sites. So it releases, in this case what will happen in the crystal lattice, it releases extra cations, okay. Cations occupying the interstitial sites in crystals, and the same number of electron goes to occupy the neighboring interstitial sites. So what will happen in the particular crystal system, there is going to be an extra cation that is being occupied in between the interstitial site. So what will happen now, the crystal lattice is being positively charged. So to maintain the electrical neutrality of the substance, some negatively charged particles is going to occupy the interstitial sites neighboring to the already occupied cations, okay. So this type of defect is also known as the Frenkel defect, and an example of this one is the zinc oxide. So next one is the metal deficiency defect. In this, a cation is going to be missed from its lattice side. So to maintain the electrical neutrality, one of the nearest metal ion is going to acquire an extra positive charge, and it will be occupied in the vacant side. And it is difficult to prepare in the stoichiometric composition, and it contains less amount of the metal as compared to the stoichiometric proportion. So the example of this type is the iron oxide. So the ions are in +2 charge in the whole crystal lattice. Some of the iron lattice sites are vacant. So to maintain the electrical neutrality, the adjacent metal atoms, that is iron, is going to acquire an extra positive charge, and it is being occupied in the vacant side. So that is what is mentioned here. In crystals of iron oxide, some Fe2 plus cations are missing, and the loss of positive charge is made up by the presence of required number of iron 3 plus ions, okay. So with this, imperfections in solid topic is going to be ended, okay. So okay, we are done with the theory part of this unit, and now we are going to see about the problems based on density and then unit cell dimension. So first we are going to solve problems based on the unit cell. These type of questions are very important for your competitive exam. So first question is, in a cubic unit cell, A atoms are at all corners, B atoms are at all face centers, and C atoms are at all edge centers, D atoms are at all body centers. So in a unit cell, they have given that A atoms, that is the corner atoms. So all the corner atoms have been filled with A atoms, and for B atoms, all the face centers have a B atom, and C atom are at all edge centers, and D atoms are at body center, okay. So everything is filled. So how many corners are there in an unit cell? 8 corners, right? So 8 atoms. And then in face center, 6 face center atoms are there, and then to 12 edge center and 1 body center, okay. So what is the contribution of the corner atoms? 1 by 8. So 8 into 1 by 8 which is equal to 1. Face centered atom 6 into 1 by 2, contribution is 1 by 2, so 3. And then H centered atom is 4, 1 by 4, contribution is 1 by 4, so this is also 3. And then body centered atom is 1, which is equal to 1. So with this values we can able to write the formula for unit cell. So for A, what is the value? 1. So A1, B3, C3 and D1. So this is the formula for unit cell. Okay, so now we'll see the next one. If 25% A, 50% B, 75% C are removed, calculate the formula for unit cell. So in the whole unit cell, we are going to remove 25% of A. So how many corner atoms are there? 8. We are going to remove 25% A, right? So answer is 2. We are going to remove 2 atoms, 2 A atoms and then B atoms. Totally 6 B atoms are there. 50% of B atoms are going to be removed. So 51s are, 52s are. So answer is 3. We are going to remove 3 atoms. And then in H center atoms, 12 atoms are there. We are going to remove 75% of C atoms. So answer is 9. We are going to remove 9 C atoms and then D atoms. So we are not going to remove any D atoms. So D atom is as such. So D atoms will be as such. Okay. So 2 atoms are going to be removed. Okay. Then what will be the remaining corner atoms? 6. Already 6 face centered atoms are there, and in that we are going to remove 3 atoms. So remaining 3 atoms will be there, and in H center 9 atoms are going to be removed, so that 3 atoms will be there, and the body center atoms are not going to be, we are not going to remove that. So what is the contribution now? 8 into 1 by 8. Okay. So answer is 3 by 4. And then face center atoms contribution is 1 by 2. So answer is 3 by 2. And then H center contribution is 1 by 4. So the answer is 3 by 4. Okay. And then the body center atoms contribution is 1. This is 1. So with these values now we can able to write the formula. A 3 by 4, B 3 by 2, C 3 by 4 and D 1. So the unit cell's formula cannot be in a fraction. So for that we are going to multiply with the highest denominator. So we are going to multiply with 4. Okay. 3 by 2 into 4, then 3 by 4 into 4 and D into 4. Okay. Now what will be the answer? A3, B6, C3 and D4. So this is the formula for unit cell in this case. Okay. So now we'll see the next one. If one edge of a unit cell is removed, then what is the formula for unit cell? So one edge is going to be removed. So how many atoms are there in an edge? 2 corner atoms and 1 edge center atom is there. So one edge is going to be removed completely. So how many corner atoms are removed? 2 corner atoms are going to be removed, right? So what will be the remaining number of atoms? 6 atoms will be there, and 1 edge center atoms is going to be removed. So 11 atoms will be there. So face center atom, 6 atoms are there, and then body center atom is 1. Okay. So now what is the contribution? 1 by 8. And then answer is 3 by 4. And then face center contribution is 1 by 2. Answer is 3. So edge center contribution is 1 by 4. So 11 by 4. And then body centered atom is 1. Okay. So with this now we will write the unit cell formula. A 3 by 4, B 3, C 11 by 4 and D 1. So again it cannot be in a fraction. We are going to multiply with the highest denominator. So A 3 by 4 into 4 and B 3 into 4. C 11 by 4 into 4 and D 1 into 4. Okay. So A 3, B 12, C 11 and D 4. So this is the unit cell formula for this question. So now we will see the next type of problems. Okay. Explain how you can determine the atomic mass of an unknown metal if you know its mass, density and the dimension of the unit cell of its crystal. So we are known with density. So we know the density and then we know the mass and then the dimension of a unit cell. So what is the dimension of the unit cell? That is the edge length A. So dimension of unit cell is nothing but edge length. cell is nothing but edge length, that is A, okay. So we know density D, mass M, edge length A. So from this what you can, and then it is also mentioned that it is for a unit cell. If we know the unit cell, we know the value of Z also, right? So what is the formula for density? Density is equal to Z M by A cube, okay. So with this formula, we can able to remember this one. With these values, we remember this formula, right? So the mass is given. And another thing is, with the help of mass, we can able to calculate the atomic mass. Mass is equal to atomic mass by Avogadro's number, okay. So this Avogadro number is a constant, okay, and Avogadro number is equal to 6.023 into 10 power 23. So this number is constant. So we know the mass value and we know the Avogadro's number, so that we can able to easily calculate the atomic mass, okay. So atomic mass can be determined by using this formula. So the next question is, the unit cell of an element of atomic mass 108 U and density 10.5 gram per centimeter cube is a cube with edge length 409 picometer. Find the type of the unit cell of the crystal, and then they have given the Avogadro's constant, okay. So what are all the things that we are known? We know about the mass, okay. Mass is, atomic mass is equal to 108 U, and we know density, which is 10.5 gram per centimeter cube, and then we know the edge length, okay. A is given 409 picometer, okay. So we have to find the type of the unit cell, that is we have to find the Z value. So if you know the Z value, we can able to find out what type of unit cell it is, okay. And we know the Avogadro's constant Na, okay. So okay, what is the formula for density now? With this we know it is based on the density. Density is equal to Zm by A cube into Na. So we are substituting the M with molar M value instead of molar mass by Avogadro's number. We are substituting this value in case of mass of unit cell, okay. So we know we have to find out the Z value. So Z is equal to D A cube Na in by M. So we know the density 10.5 into A cube, okay, edge length 409, it is in picometer, so we have to convert it into meter. So 10 power minus 12 the whole cube into the Avogadro's number 6.023 into 10 power 23 divided by molar mass, okay. So molar mass is equal to 108 U, okay. So the answer is 460. So this is the answer, okay. This is the value of Z. So 4 point, which can be rewritten as, okay, so this is approximately equal to 4, right. So we know that the cubic unit cell which have the number of atoms 4 is nothing but face centered unit cell. So the answer is, type of unit cell is face centered cubic unit cell. Okay, now we will go to the next question. So the next question is, an element X crystallizes in FCC structure. 208 gram of it has 4.2832 into 10 power 24 atoms. Calculate the edge of the unit cell if density of X is 7.2 gram per centimeter cube. So okay, we have known we are given that it is an FCC structure. So we know about the Z value. Z is equal to 4, and then the weight of the mass of each atom has been given, okay. Mass of each atom is 208 gram, which contains about 4.2832 into 10 power 24 atoms. So we have to first calculate the mass of the unit cell. So how to calculate the mass of the unit cell? Mass of unit cell is equal to, so it is given that it is an FCC structure, no. So 4 into 208 divided by 4.2832 into 10 power 24. So the answer is 1.94 into 10 power minus 24 gram. Okay, so this is the mass of the unit cell. So now we have given, they are given density. So what is the, what we have to find out? We have to find out the edge length actually. So we know the simple formula, density is equal to mass by volume. Okay, so volume is nothing but edge length cube, okay, A cube, okay, unit cell dimension cube, the whole cube. So mass we have given that 1.94 into 10 power minus 24 gram, and then so first we'll substitute this A cube in this volume, okay. So A cube is equal to mass by density. So mass is 1.94 into 10 power minus 24 divided by density 7.2. So which is equal to 27 into 10 power minus 24. Okay, so A cube is equal to 27 into 10 power minus 24. Okay, so A is equal to, we have to take square root of cube square root. Okay, so what will be the answer now? 3 into 10 power minus 8. So the value of edge length is equal to 3 into 10 power minus 8. Okay. So the fourth question is, a compound forms HCP structure. What is the total number of voids in 0.5 mole of it? So we have to calculate the total number of voids. So we have a formula for that. So in HCP structure, there are two types of voids. One is tetrahedral voids and octahedral voids. We have to calculate that individually and then we have to add that. So first we will calculate the number of particles in particles present in the 0.5 mole of it. So 1 mole contains 6.023 into 10 power 23 particles. Okay, so 0.5 mole contains 0.5 mole of substance contains how many particles? 0.5 into 6.023 into 10 power 23. So that is approximately 3.011 into 10 power 23. Okay, so the number of particles in 0.5 mole is 3.011 into 10 power 23. So the number of particles we know now. So how to calculate the number of voids? So first we have to find out the number of tetrahedral voids or tetrahedral voids. Okay. So the number of tetrahedral voids we have already seen in theory part, 2n, the formula is 2n. Okay, so 2 into 3.011 into 10 power 23. So the answer is 6.022 into 10 power 23. Okay, and then number of octahedral voids is equal to number of particles, right? So number of octahedral voids is equal to n. So this is 3.011 into 10 power 23. So total number of voids is equal to 6.022 into 10 power 23 plus 3.011 into 10 power 23. So the answer is 9.033 into 10 power 23. So the total number of voids in 0.5 mole is 9.033 into 10 power 23. So the fifth question is, examine the given defective crystal and answer the following question. So they have given a pattern of crystal structure, arrangement of particles in the crystal structure, and we have to answer by observing this. We have to answer the following questions. Okay, so by observing this pattern, what you can able to observe? So the first thing is, there is a loss in the cation here, and again there is a loss in the anion here. Okay, so from this what we can able to understand, the number of missing cations and anions are equal in numbers. So what is the first question? What type of stoichiometric defect is shown by the crystal? So the answer is Schottky defect, because in that case only the number of missing cations and anions are equal in numbers. So the answer is Schottky defect. Okay. Okay, and next is the how is the density of the crystal affected by this defect? So though the number of missing cations and anions are equal, the density of the substance is definitely going to be decreased because the particles are lost here. So definitely what will happen? The density will decrease. Okay, density will decrease. So okay, next is what type of ionic substances show such defect? So ionic solids will show this type of defect because in that only the number of cations and anions are in equal numbers and size. Okay, so ionic solids will show this type of defect. Okay, now let me see the next question. A substance form face-centered cubic crystals. Its density is 1.984 gram per centimeter cube and the length of the edge of the unit cell is 630 picometer. Calculate the molar mass. So we have known that it is FCC, that means Z is equal to 4, okay, and then the density value is given 1.984 in gram per centimeter cube, and then the edge of the unit cell A is given 630 picometer, right? So we have to calculate the molar mass now. So what is the formula? Density is equal to Zm by A cube Na. So molar mass is equal to, molar mass is nothing but atomic mass, right? So dA cube Na by Z. So what is the density? 1.984 into A cube, 630 into 10 power minus 10 the whole cube into Avogadro's number 6.023 into 10 power 23 divided by Z. So face-centered cubic crystals. So divided by 4. So the number of atoms in face-centered cubic crystals is 4, right? So the answer is, on solving all this, we will get 75 AMU, that is AMU or 75 U, okay. So this is the answer. So the 7th question is, calculate the Avogadro's constant from the following data. So what are all the topics that we have given? Density of NaCl is given, and then distance between Na plus and Cl minus in NaCl crystal is given, and then the molar mass of NaCl is given. So we know that the Avogadro's number is known, right? Na is equal to 6.023 into 10 power 23, right? So then why they are asking us to calculate the Avogadro's constant itself? So while we are substituting this value also, we have to get the same Avogadro's number, right? So for that we have to like a proof, okay. So what is the formula? Density is equal to Zm by A cube Na. So we know the density and we know Z value because NaCl, the number of atoms in NaCl crystal is 4, and we know the molar mass is given, and we don't know the A cube, that is edge length value, and we know we have to prove the Na value actually, right? So Na is equal to Zm by A cube D. So Z value is 4, molar mass value is 58.5, and then A cube is, first we have to find the A cube, right, A value, right. So A is equal to 2 into R plus plus R minus. So the distance between the Na plus and Cl minus value is alone given, right. So for that we have to find the edge length first, 2 into 281 picometer, which is 562 picometer. So but it is in picometer, right. So A cube is equal to 562 into 10 power minus 12 the whole cube, okay. So 562 into 10 power minus 12 the whole cube into density. What is the density? 2 into 2.165, okay. So on solving all this, we get 6.021 into 10 power 23. It is approximately equal to the constant value. So we have proved this answer, okay. So now I have given some important questions from your exam point of view. These questions are like reasoning questions which can be asked from this unit. So first is the define interstitials. This I have already discussed in the theory part itself. And name the compound in which the Schottky and Frenkel defects are present together. So the answer for this one is AgBr. So AgBr is the only compound which shows both Schottky and Frenkel defect. And then the next question is, why do we not observe Frenkel defect in alkali metal halides? Metal hydrides. This is because of the large size of the alkali metals, because in this case what will happen, it cannot able to fit in the interstitial sites, okay. So because of that we do not observe Frenkel defect in the alkali metal hydrides, okay. And next is mention one property which is caused due to the presence of F centers in a solid. So then in the case of metal excess defect, color is the only factor we can observe, okay. The substance will be most of the substance will be colored, okay. And next is the atoms which occupies the empty space formed in a closed packed structure is called interstitials, right. So next is the an atom at the center of an edge in a cubic unit cell contributes dash to particular unit cell. So they are asking about the contribution of the edge center atom. So this we have done already. The contribution of edge center atoms is what? 4, right? And next, the ionic solids are characterized by what? So ionic solids are characterized by the solubility of the substance, okay. And next is the account for the following. Mostly you'll be getting this type of questions only. Most questions will be the reasoning questions, okay. So the first one is glass objects excavated from ancient monuments appear milky. So this is because these objects are glass is partially amorphous and partially crystalline. So on aging, what will happen? The temperature of the substance will be varying, right? So in that case, the arrangement of particles will be it will be in a proper arrangement. So what will happen now? The transparency of the glass substance will not be seen, okay. So it will appear it appears milky, okay. And next is the zinc oxide is white at low temperature but yellow at high temperature. So we have to give reason for that. This is because zinc oxide is one of the non-stoichiometric defects. An example for non-stoichiometric defect, and most of the non-stoichiometric defects substances are colored in nature, but zinc oxide is white, okay. And then in this case, on heating, what will happen? Most of the oxygen will be lost, okay. So because of the loss of oxygen, it turns into it cannot able to form the non-stoichiometric defect, so it appears yellow in color. And next is the define packing fraction. So this is nothing but packing efficiency. They are asking about the packing efficiency. So next is the calculate the packing fraction in case of a metal crystals for body centered cubic lattice. So this I have already said in the theory part. Packing efficiency factor calculation, okay, percentage of packing efficiency, okay, in case of body centered cubic lattice. And next is the define voids. This and all I have already discussed with you guys. And then define the following terms: unit cell and coordination number. This also we have seen already. And why is graphite soft, lubricant and good conductor of electricity? So this you may get the answer in case of covalent and network solids, okay. And next is the under which situation can an amorphous substance change to a crystalline form. So on heating, amorphous substance changes into the crystalline form, okay. And explain why sodium chloride is hard but sodium metal is soft. This is because of the low, in case of sodium, the metallic bonding is very low because it contains only one valence electron, whereas the sodium chloride, it has a strong metallic bonding between the sodium ions and the chloride ion. So with this, we are done with this chapter. Okay guys, hope you have understood this chapter very well. It is a very easy chapter. Now it's your turn to read this chapter and score in your exam. So in next class, we are going to see the important topics of Unit 2 solutions. Thank you.
For more queries, please contact buddi on 98408 44987 or visit buddi.live.